All right, today we're tackling one of the most elegant tools in all of computer science, binary search. And we're going to see how it goes from being just a simple search algorithm to a super-powered way to solve some really complex problems. It's going to be fun. Okay, let's just jump right in with a massive challenge. Imagine you have a list, a sorted list, with 1 billion items in it. 1 billion. Now, how in the world do you find the one specific thing you're looking for without it taking forever? Well, you've really got two ways you can go about this. There's the slow way, which we call linear search. That's where you just check every single item, one by one. Ugh. Or there's the smart way, binary search. And with this method, you get to eliminate half the items in a single step. Yeah, it's really not even a fair fight, is it? So, to really appreciate just how brilliant our hero is, we gotta first look at the slow, painful way of doing things. Linear search is, well, it's pretty much exactly what it sounds like. It's like looking for a specific name in a giant, disorganized pile of papers. You don't have a system, you don't have a strategy, so you've got no choice but to pick up each paper one by one until you find it. And if you have 1 billion papers, yeah, that could take a while. Okay, so there has to be a better way, right? Of course there is. And it's all built on this incredibly powerful idea called divide and conquer. And that brings us to binary search. Now, this is a hyper-efficient algorithm, but it has one single, absolutely non-negotiable rule. You listening? The data has to be sorted. I can't stress this enough. The whole magic trick of dividing the problem in half, it completely falls apart if everything isn't in order. The strategy itself, though, it's just so simple, it's beautiful. All you do is jump right to the middle element. You make one comparison to see if your target is bigger or smaller. And based on that one check, you throw away half of the entire list, gone. Then you just do it again on the smaller list that's left. That's it. That's the whole thing. Okay, talking about it is one thing, but seeing it in action is where it really clicks. So let's walk through a super quick example. All right, here's our mission, should we choose to accept it. We're looking for the number 9 inside the simple sorted array. Now, if we did this the slow way, a linear search would take what? 1, 2, 3, 5 steps to find it. Let's see how our hero binary search does. Okay, step 1. We look at the whole list and jump to the middle. The midpoint is 7. We're looking for 9. Since 9 is greater than 7, we know it can't possibly be in the left half, right? So, boom, we just discard that entire section. Our search space is already down to just 3 numbers, 9, 11, and 13. And now we just do it again on our new, smaller list. The midpoint of 9, 11, 13 is 11. Well, our target, 9, is less than 11. So, you guessed it, we can throw away the right half. And just like that, we're left with only one possible number, 9. Step 3, well, the midpoint is 9. We found it, and look at that, it only took us 3 checks. Remember, the linear search would have taken 5, so even on this tiny little list, it's already way more efficient. And what's so cool is how this translates directly into code. You can see it right here. That while loop just keeps running as long as our left and right pointers haven't crossed. And those if-else statements, that's the magic. That's where we discard half the data just by scooting that left pointer up or that right pointer down. It's a perfect, clean translation of the idea we just walked through. So we know it's fast, but how fast? Like really, truly, how much better is it? This is where things get, frankly, a little bit mind-blowing. Just look at this chart. It says it all. For a list with about 1 million items, linear search to take up to 1 million operations. That bar is huge. And binary search? I mean, can you even see its bar? It's so small, it's practically invisible. This isn't just a small improvement, it's a total game changer. Get ready for this. To find any item in a list of over 1 million, the absolute maximum number of guesses you will ever need is 20. Just 20. Let that sink in for a second. 1 million items, 20 guesses. That is the power of logarithms, the power of cutting the problem in half over and over again. So in computer science terms, we call this O of log n time complexity. That log n is just the fancy way of saying it gets incredibly slowly, because of that repeated halving. And what's more, it has O of 1 space complexity, which means it uses basically no extra memory. Fast and efficient. It's pretty much the gold standard. Okay, but here's where we get to the real plot twist of our story, because it turns out binary search isn't just for finding a number in a list. That's kind of like its day job. Its secret identity is as a powerful pattern for solving a whole different class of really tricky problems.
So, let me ask you this. What if the answer you're trying to find isn't even in the list? What if you're searching for an optimal value? Something like, say, the biggest possible minimum distance you can fit between a bunch of points.
Let's look at a classic problem that shows this perfectly. It's called aggressive cows. Don't worry about the name. The goal is simple. You have some cows and some stalls, and you want to place the cows in the stalls so that the minimum distance between any two of them is as big as it can be. See? We're not looking for an index anymore. We're looking for an answer, the best possible distance. So how on earth do we binary search for that? This is where we flip the logic on its head. Instead of our midpoint being a value we compare, our midpoint becomes a potential answer that we test. We just pick a distance, any distance, and ask a simple yes or no question. Hey, is it possible to place all the cows if we say they have to have at least this much space between them? So let's try it. Let's pick a midpoint distance of, say, 4. Is it possible to place the cows with at least 4 units of space between them? We run a quick check and nope, can't be done. So what does that tell us? It means 4 is too big, and so is any distance larger than 4. So we discard that entire upper half of possibilities. Okay, so now we try a smaller distance, like 3. Is that possible? We check, and yes, it is. So now we know 3 is a valid answer, but maybe we can do even better. So we store 3 as a potential best, and now we try to find a solution in the range between 3 and 4. See how we're zeroing in on the best possible answer? And this technique, often called binary search on the answer, is what transforms this algorithm from just a simple search tool into a powerful, super flexible problem-solving framework that you can use all over the place. So, when should you reach for this tool? Well, the obvious case is on any sorted data set. But the real superpower is for problems that have this monotonic quality. That's just a fancy word for what we saw with the cows. If a certain distance is possible, any smaller distance is also definitely possible. That's the key property that lets you say yes or no and confidently throw away half your search space. And just to say it one more time, if the problem doesn't have that kind of structure or order, this whole approach is a no-go. And that really brings us to the main takeaway here. Binary search is so much more than just searching for numbers. It is a fundamental pattern for solving all sorts of complex optimization problems. So I'll leave you with this to chew on. What other problems, maybe even ones that seem impossible right now, in your own work or your own projects, could you crack wide open if you could just figure out the right way to divide them in half?